It's a great pleasure to be here. I will talk about recent joint work I did with Matej Lukic, who is a fantastic PhD student we have in Zurich. So he's this year on the job market. So if you're really looking for fantastic researcher, Matej is a great person to hire. So I will talk about this very general phenomena we have in combinatorics, which is called local to global structure. So when you try to understand something about the global structure of the graph from local properties. And the first problem which I start, it's a very classical such problem. Let me turn the clock also so that I will know that how much I talk. So it's Ramsey problem, right? And Ramsey problem says the following: you have n vertex graph G, right? For me, my graphs always will have n vertices.
Benny, can you write a little bigger? At least I don't see it very well.
I'll write a bit.
Thank you.
Bigger. No clique of size k, right? KK3, no KK or KK3. You have a graph with no clique of size k on n vertices, and you ask how large is alpha G. Right? You want to guarantee a large independent set in a graph where you know locally it doesn't have clique of size k. Right? So there are two bounds which are known for this problem. And again, in this talk, because my goal would be to improve exponents, I will not mention various log improvements of various results. I just mention the name. So it's known that in this case, the independence number of the graph G is always at least n to the power 1 over k minus 1. And we also know an example. There is G with alpha of G at most n to the power 2 over k plus 1. There is a great line of research here improving various low-order terms. Sometimes I give precise answer, and I should mention Aitai Komos-Semeredi and Kim and Bowman-Kivash and Griffiths-Moritz and Fitz-Pointiveros. But from the point of view of the exponents, that basically goes back to Erdős-Szekeres, the induction bound, and that's from the local lemma argument by Spencer. These bounds are very old, and we don't know beta exponents for k, say for k3 we know that this is the answer, but for k bigger than 3 we don't know beta exponents. Okay? So this is an example of local global. So I want to ask a more general question, but before I ask the more general question, let me give you a definition. Right? So let me denote by alpha m of G. Right? It's a minimal independent set among all m vertex subgraphs of G. Again, it's very clear what it means. You go over all m subsets of your graph, and every subset you find the largest independent set, and then you take the minimum over all subsets, right? You say, what is the worst graph, right? Worst subgraph of your graph, which have m vertices, right? And then you can ask the question again, right? It would be exactly this question: how large is alpha G if I know that alpha m of G is at least R, right? So very basic question. I tell you that every subset of size m of your graph contains an independent set of size R. You're asking how large independent set you can guarantee me in the whole graph. Now observe that, right? I'll do this here. A remark, it's indeed an extension of the Ramsey question, because if R equals 2, it's precisely equivalent to say that G is Km3. Because you're telling me that every subset of size m has edge missing. So indeed, I'm asking a question which is a more general question than the Ramsey question. And this is a question I'm going to talk about today. Now, this question was studied in various contexts over the many years. So today I will talk about the situation where I fix both M and R, and I think about the number of vertices being large. There is a different line research which was taken by Erdős and Rogers in 60s, where they said, let's fix R an independence number. So for example, I tell you that globally, your graph has independence number 5, and I ask, what is the largest subset of vertices you can find where the independence number is at most 3, right? So this is Erdős-Rogers question. And again, a lot of research was done on this question, and I want to mention maybe names of Gowers and Janser, and Rodel and Dudek. I have some work myself, Michael Krivalevich worked it, but that's not my setting today. So the question which I'm going to talk about, it's a question which was asked independently by Erdős and Heinel, and Lineal and Rabinovich, and it's always early 90s, right? 90s. And so they exactly said, so R and M fixed, alpha M of G is at least R, the number of vertices of G is N, how large should be, right? Alpha G. Right? Good. So what I'll do, so this is the question clear? Right? So that's what we're going to discuss for the whole duration of the talk. Now what I'll do, I'll tell you what is known about this question, and then I propose two new ideas. One, how to improve the lower bound for this question, and one, how to improve the upper bound. And I'll show that both of them are useful because they allow us to improve exponents, right, in the best bound which we know. So let me start with the lower bound. So this is an approach of Lineal and Rabinovich in the original paper. So again, right, my setting is alpha M is at least R, so it means every M vertices have independent vertices R. So we define K, so this would be an important parameter for this talk. It would be M divided by R minus 1 rounded down. And the key observation of Lineal and Rabinovich was that in this case, we can assume, right, I will not write it, but in this case, we can assume that G is K3. And therefore, by this Ramsey bound, which I had here, you'll get then alpha G is at least n to the power 1 over k minus 1. Okay. So why we can assume? Okay, so this is the following reason. Right? So imagine I found a clique of size k in my graph. So I put it here. Right? So this is a clique of size k. And then I found another clique of size k in my graph. And I continue doing so. So each of these is copy of kk, right? And I take R minus 1 of them. So observe that this set has R minus 1 times K bigger than M vertices, but alpha is of size at most R minus 1, a contradiction. So therefore, basically what they said that you can delete greedily these joint cliques, and once you delete R minus 2 of them, you're done. Your graph doesn't have a large clique, and therefore, you can use the Ramsey number to bound this point. Okay? So let's see how this does. Right? So the first example is when M equals 6 and R equals 3. Then you do, what is a K in this example? So the K, we said M6 divided by 3 minus 1, 2. so it's 3, right? And therefore, if my alpha 6 of G is at least 3, then Lineal and Rabinovich tell you that you find an independent set of size n to the power 1/2. And this is very good, because this is more or less the answer. Because we know by now that there are triangle-free graphs whose independence number is roughly square root n. And again, I said I would not care about that. Now think about triangle-free graph. In such a graph, if you take 6 vertices, because the graph is triangle-free, by basic Ramsey's theorem, it says that it should be independent set of size 3. And then we are done, right? So this n to the power 1/2 is actually tight because there are triangle-free graph without independence number much bigger than square root. But we already get something interesting when we go to m equals 7, right? As I said, I mostly do the examples to illustrate the ideas, and then I tell you the general results without proofs. So if m equals 7, and again r equals 3, so again you do k, and k is m divided by r minus 1, it's 3.5, and we round it down, and it's 4. So then we get that alpha 7 of the graph G. If you assume that every 7 vertices have independence number 3, it implies that independence number of your graph is at least n to the power 1/3, right? You remember always it's k minus 1. Okay? This was the problem which also Erdős-Heiner looked at. And actually they suspected, they also kind of, I think implicitly, they didn't write it in their question paper, had this argument, but they suspected that n to the power 1/3 is not an answer already for this problem, right? So this thing passing to the clique is a bit wasteful, and they actually put a conjecture, right, Erdős-Heiner, that alpha 7 of G big over T3 should apply that alpha of G is at most n to the power, is at least n power 1/3 plus x. Okay. So another example which I want to give you just to illustrate what I'm going to say next. Let's see what this approach does. Right? Another example. Let's see what this approach does if I take my m to be 2r minus 1 and r, a general r, but I want among every 2r minus 1 vertices to have an independent set of size r. Now in this case, if you take k, k is again 3 because it's 2r minus 1 divided by r minus 1, right? Let me remind you, it's m divided by r minus 1 down. And therefore, this would imply again the independence number in G is at least n to the power 1. Right? I want you to remember this thing. Actually, they would be on the board when I write next thing. Okay, so that's roughly kind of what this approach with the clique does. So what our new idea? It's actually very natural idea and quite modest. It says, while you're working with a clique, right? What you can do is you can find, right? You can start with this assumption that every n vertices of G has an independence number R, and then you prove, show that this implies that G is H3, right? You show me that G does not contain some graph H such that H has better, right, Ramsey numbers. Not necessarily concentrate on the clique. Try to understand problem maybe a bit more. Try to find other graphs H which cannot appear in your graph G. And hopefully these graphs have better Ramsey number and you can use those. And also, as I said, it's quite modest, almost obvious idea. So let me show you how fast it can give you some fruits. Obviously, I cooked my example so that to illustrate them, So this is why I showed you this example. So let's go to this example, right? So again, every 2r minus 1 vertices have independent set of size r. If we work with a clique, we have to work with the triangles, so we get this. But observe that if, right, no, that if I tell you that every 2r minus 1 vertices of your graph have independent set of size r, it implies that G is C2r minus 1 free. Right? It cannot contain an odd cycle on 2r minus 1 vertices, because this odd cycle on 2r minus 1 vertices have independence number r minus 1. So now you can say, okay, if I know that my graph is 2r minus 1 free, C2r minus 1 free, what I can say about independence number, and you can go and check the literature. This is not a new result, and then you get that the independence number of your graph is at least n to the 1 minus 1 over r, right? And you suddenly get a big improvement, right? Instead of exponent half, you get exponent which is almost 1. Okay? But that's kind of a cheap observation, but it gives you the idea, right? So now I want to go to the conjecture of Erdős and Heinel, and I try to understand if I have in every 7 vertices an independent set of size 3, what it tells me about the graph. And apparently, so this is a claim we proved. It's not a very difficult claim, but that's what we need. So if I tell you that independence, so every 7 vertices have independent set of size 3, then I can deduce that G is K4 free. But that is before, that's already was observation of linear Rabinowitz, but I also know that it's H free and H free for the following graph H. So you take like 2 triangles connected, right? So 2 triangles like that in this vertex. You take another 2 triangles like that. Right, so maybe let me draw it a bit better. And you put H between them, right? So this is my graph H. So you can forbid an additional thing like that. It's not a very difficult lemma, but it appears that this is a correct graph because it's actually equivalent. Even more you can show, right? So if every 7 vertices have independent set of size 3, you don't have K4, but you also don't have such graph H. And then we studied the Ramsey number of this graph H, obviously, versus independent set. And what we proved is that, so here is a theorem, like with Hukich and myself. We said that if alpha 7 of G is at least 3, right? So if every 7 vertices have independent set of size 3, then G has independent set of size n to the power 5 over 12 plus a little over 1, or actually minus a little over. It's minus, right? So this is proves this conjecture of Erdős and Heinel, right? Obviously, 1/3 is 4 over 12, so we get an exponent improvement over just the curve. So this is a kind of a result which I want to mention. Now, what we can do, right? And right, I will not show you. Maybe I don't think I will have a time. But so that basically was our idea, and so then we push it further in a full generality. And what we made, any questions, by the way? And what we managed to obtain is a more general result. So here is a theorem. Right? So you remember I have R, M, and then I denote by K, M divided by R minus 1, rounded up. Right? And suppose I know that every n vertices of G have independence number R. So I know to improve this approach, which is based on clicking half of the values of n. So what does it mean? So suppose I have this, and suppose my M is at most k minus half times r minus 1, right? So then I know that my independence number should be at least as big as n to the power 1 divided by k minus 3 halves, right? Although it looks for you like a small thing, again, it's an improvement in the exponent, right? Before I had k minus 1, and now I have 1 over k minus 3 halves, right? So there are a couple of remarks which I want to make. So first of all, one cannot hope to improve this too much. In particular, unless you improve the bounds of Erdős and Szekeres, you will never be able to put here k minus 2, better than k minus 2. So 1 over k minus 2 is the limit of any improvement unless you improve the classical Ramsey numbers, which we obviously don't know. Otherwise, I would give a different talk. Now, another thing, why I claim that we do half of the range, because if you look on the definition of k, so k is m divided by r minus 1 rounded up, so you notice that your m is between k minus 1 times r minus 1 and k times r minus 1. And for half of the range, right, up to k minus 1 minus half, up to k minus half, we have an improvement. After that, unfortunately, we didn't found these graphs which can help us to improve the bound of linear Rabinowitz. So in half of the range, we improve them, but in half of the range, we don't. Right? So that's the general result, right? So any questions? So, but that's a kind of a key idea, right? You want to work with this problem. I tell you locally your independence number. You obviously, it immediately forbids you certain clicks, but it actually forbids you much more. So go and try to understand what else it forbids you. Many times you can find some other interesting graphs, nature like this graph H, which it forbids. Then you can use the Ramsey numbers of this graph. So first of all, it leads to exciting new problems because these Ramsey numbers of this graph, it's a kind of cool Ramsey problems, are interesting ideas you can put in the proof. And then you study the Ramsey numbers of this graph and you get a better bound for this very nature question. Okay. So this is about a lower bound, right? So now let me tell you a few words about the upper bound, right? So the lower bound was the following. I know that, for example, every 7 vertices have independent set of size 3. What independent set I can guarantee you in the graph? Now the upper bound, it's obviously a construction. Again, I tell you, every 7 vertices in your graph have an independent set inside of size 3. I want to construct a graph which has this property, which does not have a large independent set. Right? And the question is, what can I guarantee now? So now let me move to the upper bound. So again, I'll start with approach of like upper bound, linear and Rabinowitz. And then I'll give you some additional ideas one can put to improve. So let me start as an example, the case m equals 8 and r equals 3. So alpha 8 of g is at least 3. So I want a graph in which every 8 vertices have independence number 3, but which does not have big independence number. So the observation of which one can use, so this is a simple claim, that any graph H on 8 vertices, with alpha H smaller than 3 has at least 12 edges. Right? This is a 2-1 theorem. You take, and the extremal graph, it's a union of 2 cases. Right? So that's what linear and Rabinowitz said. So observe that in order not to have this property alpha 8 of G bigger than 3, you need to have some set which has at least 12 edges. So what they said, let's take an appropriate random graph, and I write you now a statement where every 8 vertices spend less than 12 edges. So then it's automatically will have H3 property, right? Every 8 vertices will have an independent set of size 3, and this the independent set in the random graph we know is usually not very big, and that would be a construction. So let me give you a lemma, which you can prove using an appropriately defined random graphs and local lemma, which says the following. So you fix a collection, finite collection of graphs, H1 up to HT. T can be any number fixed. And you fix an, you look on the quantity, and every graph HI, you take a two density, I mean, kind of an expression of which works, which is appears in two densities. So you take number of edges minus 1 divided by the number of vertices minus 2. And suppose all these numbers are bounded away by n, right? So this is your setting. You have a set of forbidden graphs. They all satisfy this inequality. So then there is n vertex G, which is H3, so it does not contain anybody from this family, and alpha G is at most n to the power 1 over n. Now, I slightly cheating here, there is some polylog terms there, which I'm not writing, but again, as I said, for this talk, I'm mostly interested in improving the exponents. So I always
Benny, sorry, is the inequality for the number of edges over the number of vertices in the other direction?
Maybe, right?
You want to forbid dense graphs, not sparse graphs.
I want to forbid. Right. So I take maximum, right? So think about this. So n is a maximum if you want a minimum. So n is a minimum of this, right? Right. Minimum of this is n, right? That's right. It's another direction, right? If you want, right? It's another direction. What forbid dense, right? No. So. Right, so if,
yeah, now it looks good. Now it looks good.
Right. If my graph has more edges, then I know that I take an appropriate random graph. I will not have any of them, and I will have independence. Okay. So that's basically a very general result, which they used, proved by local lemma. And now you can try to write a corollary. Right? So there is G with alpha 8 of G is at least 3, and alpha of G, for example, in this particular case, would be at most n to the 6 over the 1. I'll say in a second about this. So why this is true, right? So you use this claim, right? Proof. You compute, right? You know that you can guarantee, right? You're trying to forbid graph with 12 edges, all the graphs, right? It's finitely many, with 12 edges on 8 vertices. So this quantity, right, E of H minus 1 divided by H minus 2, in your case, would be 12 minus 1 divided by 8 minus 2. It's 11 over 6. So then you can find a graph where every 8 vertices spend less than 12 edges, so it will satisfy alpha A of G is at least 3, and its independence number. Now, this is, for this particular H3, just an illustration. This is obviously not the best thing you can do. So observe that you can put here n to the 1/2 from 6-3 case, right? I already told you that there is a graph where every 6 vertices have independence number 3, which does not have independent number, whose biggest independence number is n to the 1/2. But that's kind of illustrates you an idea what you can do. So let me show you another example where actually right, which people actually use as a benchmark for various techniques to attack this problem, right? Whereas this maybe would be a bit more interesting because there would be no such improvement like 6-3. So the example is where M is, say, 20 and R is 5, right? Then K in this case, M divided by R minus 1 rounded down is 5. Right? So then again, using this approach of linear and Probabilistic, you ask how many edges I need to have, right? So that I guarantee, what is the maximal number of edges I need to have so that, you know, my independence number is smaller than 5, right? The smaller than 5. So you take a 2-1 graph. So this is like 4 of them, and this is K5, right? And it has 40 edges. And now you know that if every 20 vertices have at most 39 edges, you have independent set of size 5, right? Right. So therefore, like using this argument, right, you again take this E of H minus 1 divided by H minus 2. So in this case, it would be 39 over 18. And so you get that there is graph with alpha 20 of G at least 5 and alpha of G at most n to the power 18 over 13. Now, this exponent was approved over the years, so maybe let me tell you because I think this is interesting, right? So this gives you 2.17, this number. And then Krivalevich then after that Kostolka and Yancey, right. So they improved this kind of exponent to 1 over 2.36, and then Kostolka and Yancey improved it further to 2.39, right? The exponents of this in the upper bound. And what they did, they, instead of looking on a Turing problem, they asked, okay, we know that, you know, this graph does not, we want a graph which does not have independence number 5. So let's look on the results on the number of edges in color critical graph. So these results can be used to kind of get a little bit better bound on how dense should be the forbidden graph. And that's how they achieved this result. And I'm mentioning that because it's a kind of interesting benchmark problem, because I want to say something what the tools I'm proposing can achieve for it, right? So again, on every 20 vertices, independent set of size 5, the exponents were first 1 over 2.17, 1 over 2.36, 1 over 2.39. Finally, let me tell you that in general, right? So you understood the approach, right? So the approach was you look on the graph, you say in order it to violate this MR property, it needs to be sufficiently dense. Let's take a random graph where such dense graphs do not appear, calculate its independence number, it will give us a construction. So in general, if you do this, right, and this was done in a paper of Linear and Rabinovich, you get the following theorem, right? Linear and Rabinovich, which says that if I tell you that every n vertices of G has independence number R, right? And I define my K, and I remind you that K was M divided by R minus 1 down. Then there is G with this property, and alpha G most n to the power 1 over I think a minus 2 over k minus 1. And from where this 2 over k minus 1 comes from, so we can roughly have a computation. So I will give you a kind of pseudo proof, right? So again, we look on a Turan graph, and for Turan graph, we want to compute this quantity. And now, what is a Turan graph? Turan graph in this case is roughly, you remember, it's a union of cliques of size k, and you have r minus 1 of them. Right? And if you compute this quantity, so it will be k choose 2 times r minus 1, and the total number of vertices is k times r minus 1 minus 2. And this is approximately 2 over k. So that's basically what you get with this approach. Meaning, what it proposes is a kind of illusion of this, but I think it leads to a really cool new problem we have in study. This is a problem.
You have some problems with your microphone, I think.
So we propose.
Benny, the last equality is not right. It's the inverse.
Right, it's in inverse, right. And then, the last equality is not right. It's inverse.
Like instead an arrow.
Right, this is m. This is my m. Right. This is my m, and then exponent is 1 over. Very good math. Excellent. Amazing. People actually listening. That's great. So here is a kind of a small thing which we propose. And it's well known for people who do random graphs is that in order to forbid a graph, it's not necessarily always good to work with this quantity kind of two density of the graph itself. Sometimes it has a denser subgraphs, and therefore you can guarantee that you forbid these denser subgraphs, and in particular, you forbid the graph itself. So for example, instead of forbidding K4 plus a pendant edge, you observe that it's much kind of easier for you to forbid K4. For that, you can take a denser random graph and produce a better result. So therefore, a natural thing here is the following. So let me remind you the definition of two density. Two density of graph H is denoted by M2H. It's a maximal over all subgraphs of H with at least 3 vertices of this quantity E of H prime minus 1 divided by H prime minus 2. And so if you want to do this approach, right, that's basically the only kind of new but important thing which we say. If you want to do this approach, and this is more or less a natural approach to do, you want to ask the following question, right? Sorry, let me give you one more definition and then the question. So let me define MR. It's a minimal two density of a graph H with number of vertices M and alpha H at most R minus 1. So you ask, okay, suppose I have an vertex graph and it doesn't have independent set of size R. This is a guy I don't want to appear, right? If I don't have any such guy H in my graph, then every n vertices have independence number. I want to ask, and this is a question we propose, this is a new question. We want to know, right? We want to know this. What is MR, right? So we want to minimize the two density over all graphs with independence number minus 1. So it's a kind of a Turan type problem, but for two density. Right? And why we want to know this? Because exactly as I said before, if you use random graphs and local lemma, you get the following proposition. Right? So there is graph with alpha m of g is at most, is at least r, and alpha of g is at most n to the power 1 over m mr. So this number which you can put me there, you can put in the exponent 1 over this number of the independent set, which you kind of an upper bound on the independent set of your graph, right? So that's a kind of a new idea which I want you to take from this talk, right? Instead of looking in particular Turan graph, or Michael and Sasha, they looked on some other bounds, but they basically kind of were looking on the initial set of vertices. So we're suggesting, okay, look at the graphs which do not have an independent number. They have a crossing. Okay, so if anything, let me tell you. So what we're proposing is that study these graphs H on m vertices with independent number r minus 1, and look which of them, like what subgraph they should have. Maybe you always have a subgraph which has a big 2 density, and because of that, you can forbid them all much cheaper. Okay? Right? So you will forbid them in much denser random graphs, and these denser random graphs, which obviously have smaller independence. Okay, so far it's obviously I'm head wavy, and I need to persuade you that this is an interesting problem, and also that it's useful for my original question. Right? And so let's keep this, and maybe let's look on some new results we can produce. So let's first start with m equals 8 and r equals 3. And you remember that Turan was giving me upper bound on the independence number, right? N to the 6 over 11. And then I say, even if you take into account the 6-3 problem, that you don't have triangle-free graphs with independence number much bigger than square root, then you get square root. So what I can do now with this thing, right? So the claim which I want to prove that, right? Claim that M83 is at least 5 over 2, right? Which means that every graph on 8 vertices which does not have independence number 3 has 2 density at least 5 over 2. And so therefore, I will have graphs G with alpha 8 of G at least 3, and alpha of G is at most n to the 2/5, which is 0.4, so it's already better than 611, it's also better than that. It's quite sizable. And the proof is very simple in this particular case, just to illustrate, right? What is the proof of this result? So there are 2 things which I observe. So the first of all, I say if, right? So let H, right? So H is 8 vertex graph with alpha H at most 2, right? And then I should show you that its 2 densities 5 over 2. Right, so there are 2 things which I observed. If H contains K4, then we're done. Why? Because already the 2 density of K4 has 6 edges and 4 vertices, right? So then 6 minus 1 divided by 4 minus 2, it's exactly 5 over 2. So this is already kills you. So now I can assume that K4 is not appear in my graph H. Then you take a vertex B, right? And you look on non-neighbors of B, right? So this is a set of of H, right? So this is VH minus V minus the neighborhood, right? Now observe that you cannot have a non-H here. Why? Because a non-H here together with V gives you independence number 3. So you know that this guy should be a clique. And also you know that it cannot be K4. So you know that here there are at most 3 vertices. So because of that, if no neighbors of V have at most 3 vertices, I know that the degree of V, right, so total I have 8, 3 is here, 1 is here, so degree of V is at least 4. And if the degree of V is at least 4, the total number of vertices in H is 4 times 8, 32 divided by 2, 60. And now you do exactly the same thing. You take 16 minus 1, right? You do, is it bottom visible? I write it and then you tell me. 16 minus 1 divided
It is visible.
8 minus 2, which is 15 over 6, which is exactly 5. Right? So it's not even was very difficult for us to prove for small cases this to density, and it gave us quite sizable improvement. Right? So you can show that every graph which does not contain independent set of size 0 and 8 vertices has to density 5 over 2, and therefore you can get a better construction. And actually, here the 5 over 2 is an answer. There is a construction which you can do. Now let me maybe mention this benchmark problem. I just don't do the proof, but I just want to kind of tell you the result. Okay. So the example which I mentioned. So you can show that M25, so again, you're asking, graph on 20 vertices doesn't have independent set of size 5. What is the 2 density should have? The minimal 2 density. You can show that this is 3. Right? So in particular, it would imply that there exists G such that alpha 20 of G is at least 5. And alpha of G is at most n to the power 1/3. Right? And you remember that instead of 1 over 3, the previous was 123.9. Right? So again, it's a good improvement. Now, let me tell you what we can do maybe in general. Right? So first of all, right, I think it's a very interesting problem, right? So, and I mentioned it again in there, right? I give you a graph, I tell you independence number, but now you're not like in Turan problem trying to minimize the number of edges, but you're trying to see what is the 2 density over all, right? The minimal 2 density which you can guarantee. So in general, we cannot solve this problem, right? We, for example, managed to solve it for R equals 3, right? For all like 8-3 or I don't know 25-3, we know what is the minimal 2 density you can get. But in general, we don't know how to solve it, but we know how to estimate. And the theorem which we get is the following. Right? This is theorem, this is Matthew Vukic and myself, which says the following. So you again have MR fixed. Right? Let me remind you that K is M divided by R minus 1 rounded. So then we show that there exists M vertex graph G, in which indeed every M vertices have independent number R, and whose independence number is at most n to the power 2 over k plus 1. Right? So again, instead of 2 over k minus 1, right, which was here before, we can get 2 over k plus 1. Right? Looks not much, but that's kind of right. It's an improvement really an exponent. Maybe to kind of tell you a bit more about this result, in particular our proof and the way we're doing it shows that you cannot get. We have some error term, right? Some small error term. Also, Nati and Vitinina and Rabinovich also had some small error term, but this is the main thing. And what we can say, right, and you see this from the proof, you cannot improve this 2 over k plus 1 without improving the upper bound for Ramsey number. Now this is really, we're not even halfway through. So if you can do better than that, you in particular do better than classical Ramsey numbers as well. Right? So you basically plot this bound to the level of plus. Okay, so that's basically all I wanted to tell you from the point of view of ideas, right? So for the lower bound, the idea was you study your problem. I tell you every m vertex has an independent set of size R. You try to understand which other graphs H do not appear in your graph G. Obviously, cliques of certain size, but maybe some other graphs H, and these graphs H can have better Ramsey numbers than cliques. You prove this. For the upper bound, we try to do the usual approach, right? You take an appropriate random graph, and you guarantee that in this random graph, every m vertices have independence number R, and there is no big independent set. And if you do on mathematics, you need to choose your H probability certain way, and it leads to the following problem, right? And again, I want to mention this as a first, maybe open problem. I want you to think that I think this is, as extremal problem is pretty interesting and leads to interesting constructions, right? So this is a problem number 1 in my list, which says find a minimum two density. And let me remind you, it's again E of H minus 1, H minus 2 over all subgraphs, of a M vertex graph with alpha of most R minus 1. So that's question. Find it, characterize extremal examples. We know to solve it, right? We know for R equals 3. We have some we have some estimates in general, but I think it's a very interesting question. This is problem number 1. So problem number 2, like the 7, 3, which I already mentioned. So we improve the lower bound. So in particular, for the upper bound, we don't have an improvement, right? So if you want a graph where every 7 vertices have independent set of size 3, the only construction I can propose, you take a triangle-free graph with independence number square root n. Obviously, every 6 vertices in this graph have independence number 3, so even 7 will have independence number 3. So in particular, the question which I want to ask, is there G with alpha 7 of G at least 3, and alpha of G is at most n to the 1/2 minus x. I think if you look on the paper of Heinel and Erdős, they believe that the answer is yes. That actually was the second question which they asked. Their conjecture was that 7, 3 is firmly the exponent between 1/3 and 1/2. So we know that it's not 1/3, we proved it. So this thing remains open, right, to show that it's actually not. And the problem number 3, which I want to propose, and obviously, right, I prefer to be very specific because then it's easier to see. Our improvement of the lower bound improves 7, 3, but it says nothing about 8, 3, right? So if alpha 8 of G is at least 3, shows that alpha of G is at least bigger n to the power 1/3 plus x. So 1/3 will come from the fact that this implies that your graph is K for 3. But it looks like that you should be able to do better. That's what at least looked for us when we think about this problem. We couldn't prove it, but I think it's a very interesting working question. And I think I stop here. Thank you.
Thank you very much. Very nice talk. Yeah, I think that we are out of time, but probably one question. Does anyone have? About the general results that you give in the end is so the idea is the same as you do for this in this particular.
For the specific things, it's just more involved estimates. Like for upper bound, you need to solve this true density problem, which you can solve asymptotically. For lower bound, you kind of have some interesting iteration where you can kind of feed this bounds which we have for M3 problem, right? Every M versus have independence number 3 for the general case. But it's involved, I would not be able to tell you. You can look in the paper and see how it goes. But the idea is all here. That's what basically.
Yes. Any other questions? Okay, if no, thank you again. Very nice talk. Thanks. We have
Thank you, Benny.
2 minutes break before the next talk.
Thank you. Thank you, everybody. Bye.